Here's a quick video introducing exponential growth. Exponential growth is a whole big topic, has tons of applications in finance and biology, but here's what I'd like to chat with you quickly about. There are a couple of different sort of standard models of exponential growth. One is you have a constant times a base to an exponent. So let's look over in Desmos what that looks like. Okay, so let's imagine you had the function 5 times, say, 1.4, 1.4 to the x. Okay, what would you expect to see there? Well, the constant is what happens when x is 0. Now, often what we do is we actually don't use an x. I think it's most common actually to see a t there. And if you're going to use t, you have to make it a function explicitly. Desmos doesn't guess right then. And what happens? Well, this would be what happens if you have a 40% increase in your population every year, say. Well, so watch what happens here. 1.4 is really like 1 plus 0.4. 0.40 is 40%. And so this says, hey, after 1 year, when t equals 1, you get your 5 initial back, plus you get 40% more, that's 2. And you can sort of see what happens there. It grows faster and faster. And I can zoom out, and you can see how it grows faster and faster and faster. And sometimes you might think, well, negative values don't really make sense, but they really do. Let's imagine you discover that you have 500 bed bugs. Oh, the excitement. Maybe I ought to change my my limits here so you can actually see 500. Okay, there's 500. At time 0, we had 500. And I really want to know, hey, what would have happened if I had dealt with those 500 bed bugs 5 days ago? And so you can sort of see here, this point at -5, that says, well, this model says you would have had about 93 bed bugs 5 days ago. And if you'd have dealt with it 10 days ago, right? So negative time just means in the past, so on. And this model says maybe bed bugs got introduced maybe a little over 2 weeks ago. So that's one model that is helpful, shows up in most textbooks. This is another model. This model focuses on a base of 2, okay? So a base of 2 means you're doubling, and then they have a k there. Well, let's imagine we want to think sort of in terms of doubling, and we want to think of something like this. Here's our bed bugs, since we already have those up. Maybe you want to put 0.14 there. Maybe that's the constant k. Did we use a k there? Doesn't really matter what's there. The constant k that I want to use. And then you could look at a model that's similar, see 500, and then we could say, okay, what happens? Well, after 5 days, you're up to 800. And what happens if this number comes down to 10%? Well, it's going lower, right? And if it was only 0.002 or 0.003, now it's growing really slowly, right? I just want to emphasize in the long term, it's still going up and it's still curving that same direction, but it takes a lot longer, okay? As long as we're here, why not just also mention, so exponential growth is the topic of this, but if this number happened to be negative 0.2, you'd actually have an exponential decay model. Really, the big difference between exponential growth and exponential decay is whether you have a negative coefficient there. One last model I'd like to chat about, and that is this model, c times 2 to the t over d. And d is the doubling time. So a lot of times in biological populations, you know that you have 100 gazelles to start with, and you introduce them to a new island, and you have something that says t divided by 15. Well, let's look and see what happens with this model. You start with 100. What happens at 15? Well, at 15, can you see we're exactly at 200? Why is that? Well, because when t is 15, you have 15 fifteenths. That's 1. 2 to the 1 is doubling. Well, what happens, and we could even do a little table action here. Nope. Table. I suppose I'd have to call my function. Oh, I think I can do that. Let's call this f of t, just so they can work there with us. And then you could say, hey, at 0, right, f of, that's 100 at time 0. At 1, you can see we're a little bit higher, but at 15, you're up to 200. What happens at 30 years? Well, the population is doubled again. And 45 years, the population is doubled again. And all of a sudden, even though gazelles are so pretty, they start to be a pest. So those all are different ways of describing things. But when you're concerned about the doubling time, you have that number down there, by the way, so similar to the half-life formula, except for notice there's no negative there. But all of those are exponential growth models. You can model any population or amount of money with any of those models. Some are just more convenient than others.